Okay, and we're going to continue with this problem. Of course, we know that here we have no, can you listen to me? Can you see me, people? People, can you see me? Can you hear me?
Yes, doctor.
Okay, thanks. So here I have no translation, no rotation. Here I have a force downwards and no moment. Okay, so immediately we see that here I have F1y, M1z, I have minus F, and I have 0. I have the equation here, I'm sorry, the matrix, and here I have 0 and 0. So these are unknown. And here I have D1y, I'm sorry, D2y, and phi 2z. There. So we separate, remember? Okay, so the first subsystem, remember, is the unknown displacements. So we take this part here because this is multiplied by 0, and we say this is minus F 0, and then we have here EI over L cubed. It's a 4x4 matrix. I'm going to give you the values here. It's 12. Let me go back just to check. Here is this part here. 12 minus 6L and 4L squared. This multiplied by D2y and phi 2z. Anybody? Determinant of this? Determinant of this? Anybody? Determinant of this? No. Determinant? Miss Pinkai, what's determinant of this matrix?
But I don't remember how to get the.
Come on. It's the product of this minus this.
12 L squared.
So it's going to be 48 minus 36. So it's going to be 12 L squared and multiplied by this term. So it's different than 0. So if that's different than 0, that means that we can solve the system and the solution is going to be unique. These three things are equivalent. Remember your your numerical analysis class. So we can solve it, and we can say that so it's D1y and phi 1z is going to be equal to minus 4FL cubed over 12 EI. And the other is minus 6L squared over 12 EI. Units always F L cubed. EI, units of EI, it's FL squared. So we are fine. And here we have FL squared over FL squared. So this is non-dimensional. So we're fine. We're fine. Okay. Next step is the second part of the other equations that we didn't consider in the first part. So that means that we need to find these two forces. Okay. Let's check so far. The sign, both are negative. Okay. That means that, let me go back here. If we make a sketch, is going to be like this. And you see that this is the deflection downwards, and the rotation is like that. If this is X, this is Y, okay? Counterclockwise is positive. This is negative. So, see, that's the thing, that it's not only calculating things, it's just all the time checking. Please remember, before we go to the evaluation, I don't have to tell you. This is something that we have agreed. Every time you calculate, you have to say why you think this is correct. Every time. So that's something that we need to do. It's just a way of working. Okay? Now, let's go to the second part of the solution, of the second subsystem. See, these are the two. This is number 2, right? So these are the displacement of the second joint. The displacement of the first joint are 0. So right now, we know all displacements of the system. What we do in the second part of the solution is, since this vector is completely known, we multiply by the first 2 lines. Of course, these 2 are 0. So the only part that we are going to consider is this thing here. Okay, let me go back. I have minus 12 and 6L. So here, so it's going to be minus 12, and this is 6L. And we see here that this is 4 over 12, this is 6 over 12. So we do this multiplication, and the result is going to be that we get reactions. Remember, the reactions are external forces in the points of support. Okay? And the result is going to be, let's do it. It's minus 12 and 6L. So F1y is going to be minus 12. This is FL squared over 12EI. Okay, so this is common, except this is minus 4L. So this is multiplied by minus 4L. And the other term is 6L. So it's going to be plus 6L multiplied by 6. Oh, minus. There. So I have 48, 36. So the result is going to be plus 12, and this plus 12 cancels. So the result is going to be, damn it, F, and that's it. Because, yeah, because this is, these terms here are multiplied by EI over L cubed. There. So we cancel EI, we cancel L cubed, and we got F. Make sense? Mr. Carrion, does it make sense? Mr. Carrion, are you there? No. Mr. Ramon, does it make sense? Mr. Ramon, Jürgen Ramon?
Good morning, doctor.
I don't want you to be polite. I just want to say something. Does it make sense or not?
Doctor, do you listen to me?
Yes, I can
Okay.
listen.
Okay. Repeat me the question, please.
No, forget it. If you're not here, not here. I'm sorry. Mr. Peralta, are you here?
Yes, doctor.
Does it make sense?
I think that it makes sense.
Why?
Because it's a linear problem, and if
No, that's not the reason. That's not the reason. You're saying that F1 is F. Does it make sense? Miss Lopez, does it make sense? Miss Lopez?
No, because the force is negative.
Yeah, but where are you calculating this force? This force is F1y.
it's because
Just a
it's
second, yeah, just a second. One by one. Right now, Miss Lopez is talking. Miss Lopez, go on. No?
The determinant is, or the matrix is.
No. I'm saying is that if this result makes sense or not, that's what I'm asking.
Yes.
Why?
But the force, the force is negative.
I know. Mr. Nevares, are you there?
Yes, good morning.
Does it
yeah,
make sense?
It makes sense. Yes, it makes sense because you already get the sign in the first matrix.
Exactly. See, you're applying this force in here. So if you want to have equilibrium, this force points downwards. You need a positive force here in order to have equilibrium. So this force upward cancels this one. Remember, F1y is an external force. External force. Okay, and we can calculate, I'm not going to do it, but you have to do it. You can calculate M1z. That's going to be FL. And I'm going to put these points here, meaning that you have to do it at home. Okay? And again, makes sense because if you have a force upward here, the thing will rotate in that direction. So you need a moment, an external moment in the opposite direction. And counterclockwise, you see this is X, this is Y. Counterclockwise is positive. So you are applying a moment like this, which is positive. So it makes sense. People, any questions? Anybody? No? Okay. Let's do bending moment. I'm sorry, shear force. Just use this one here. Shear force. Everybody, please apply this formulation. Okay, let's apply this formulation. The shear force is constant, as we said. The first two terms are 0. So let's evaluate this. Okay. So it's going to be 12 minus 6L. So remember, because of the assumption, this is uniform. So it's going to be EI over L cubed. The first two terms are 0, the other are different than 0. And these two terms, let me go back because I forgot here. It's minus 12 and 6L. So I have here minus 12 and 6L. And then we have something here, but just multiply by 0. So V at X is going to be EI over L cubed. And the two displacement here are already calculated in the previous slide. Here, I have minus 4 L cubed over 12. So I have minus 12 multiplied by minus 4 F L cubed over 12 EI plus 6L multiplied by phi 2 here, minus 6 over 12. There. Oh, man. I got 48 minus 36, that's 12, divided by 12, that's 1. This is positive, this is negative, so this is equal to F. So it is constant. If we see this analytically, you see, this is a reaction. If I make a cut here, the shear force is going to be downward. It should be negative, and there is an error somewhere. Let me check. Here. Oh, this negative is missing. I'm missing this. I'm missing this negative here. So the shear force is equal to minus F, and this is correct. So in this case, the solution is exact. Why? If you have this equation, this problem, Mr. Wacon, what's P of X to solve the beam problem? What's P of X? Mr. Wacon, are you there? Mr. Wacon, are you there? No? Ms. Kumbe, what's P of X to solve this equation exactly, analytically? What's P of X, Miss Kumbe? What's P of X? What's the load per unit length of this problem, P of X? No. Let me write it again here. The analytic solution, well, let me erase this. The analytic solution corresponds to this. EI, the fourth derivative, is equal to P of X. I'm asking you, what is this? Ms. Kumbe, what is this?
F.
Yeah, but what is in this problem? In this problem, this is the problem that we're solving.
F.
No, no,
0.
because F is in the boundary. So in this case, P of X is exactly 0, as somebody said. So what shape does V of X has? If you integrate this with this equal to 0, what's the solution for V? What's the mathematical distribution of V? What's the function for V?
Q, question Q.
Exactly, exactly. This is a cubic polynomial. And that's exactly that we're assuming to approximate the solution. That's why in cases when you have no distributed load and you put joints where you apply forces or moments, the solution is going to be exact. Because we are approximating the solution with a cubic polynomial, and that corresponds exactly to the analytic solution. Okay, people, any questions? Any questions? No? Okay, we're going to have we're going to have a break here. And then when we continue, we will go on with an example with two elements, okay, just to generalize things, okay, aligned elements. Let's take a break.